You know, I was thinking about the quietest winter night you can imagine. Just total silence. Now picture that, but at the South Pole.
The most isolated place on Earth.
Exactly. And today we're doing a deep dive into some reports on something buried under all that ice. It's a telescope that doesn't look up at the sky.
It looks down.
It looks down into the ice to see the entire universe. It's called the IceCube Neutrino Observatory.
And it really is something out of science fiction. The whole idea that to see the cosmos, you have to bury your observatory a mile deep in Antarctic ice.
The scale of it is just hard to get your head around. It's not one big lens. We're talking about, what, over 5,000 individual sensors?
Over 5,000, yeah. They call them digital optical modules, or DOMs. And they're suspended in this perfect, dark, clear ice between about 1,450 and 2,450 meters deep.
Just a giant frozen grid, and getting them down there. I mean, the reports of the construction were incredible.
Oh, the engineering was a marvel. You can't just drill into ice that deep with a normal rig.
Right, the hot water drill. That part was wild. They essentially melted these perfectly vertical holes, 2 kilometers deep.
And then it was a race against time. They had to lower these long strings of sensors before the water in the shaft refroze around them.
All during that tiny window of the Antarctic summer.
Exactly. November to February. That's it. If they missed it, the hole would be gone. But what they built is basically a perfect trap.
A trap for what they call ghost particles, neutrinos.
Cosmic messengers is a better term, because unlike light or other particles, they just don't interact with anything.
So they aren't bent by magnetic fields or blocked by dust. They fly in a perfectly straight line from whatever created them.
Right. Straight from a black hole or an exploding star for billions of years, right to us. The problem is, because they pass through everything.
They're almost impossible to catch.
Almost. And that's where the ice comes in. It's all about something called Cherenkov radiation.
Okay, so this is the part that bends your brain a little. We all know nothing is faster than the speed of light.
In a vacuum, yes. But light actually slows down when it passes through a medium, like water or ice.
Right.
So when one of these high-energy neutrinos finally, very rarely, hits an atom in the ice, it creates another particle, a muon, that's going so fast, it's actually faster than the speed of light in the ice.
And that creates a kind of a shock wave.
A shock wave of faint blue light. Think of a boat going faster than the waves it's making. It creates a V-shaped wake. This is like a cone of light.
A bow shock of light. So the thousands of sensors are just waiting in the dark for that one tiny flash.
And by timing which sensors see the flash and when, they can reconstruct the path of that particle all the way back to its source. It takes, a ton of intelligence to process that.
Speaking of intelligence, this seems like a good time to mention our sponsor, Embersilk.
Yeah, if your business is looking into AI, how to train it, how to use it, they're the ones to talk to.
They can help you figure out where AI agents could make the biggest impact for your business or even just your personal life. Check them out at embersilk.com.
It's definitely worth a look.
So back to the ice. This giant frozen detector. Has it actually caught anything interesting?
Oh, it has. The first huge breakthrough was in 2013. They detected 28 extremely high-energy neutrinos from outside our solar system.
And the scientists, I love this, they nicknamed the 2 highest energy ones Bert and Ernie.
They did. And a later one that was even more powerful, they called Big Bird.
Huh. But beyond the fun names, that data led to something truly historic in 2018, right? With a blazar.
Yes, a blazar called TXS 0506 plus 056. For the first time ever, they traced a single high-energy neutrino back to its specific source.
And that source was a supermassive black hole, 3.7 billion light years away, that was shooting a jet of particles almost directly at us.
It was a game changer. The birth of what we call multi-messenger astronomy. We're not just looking at the universe in light anymore. We're using particles, gravity waves. We're getting a much fuller picture.
It's like we've developed a whole new sense to perceive the universe.
We really have.
Yeah.
And it's just getting started. Just last year, they released a map of our own galaxy, the Milky Way, made entirely from neutrinos.
Wow.
They're even using it to hunt for dark matter. The theory is that particles of dark matter might get caught in the sun's core and annihilate, sending out neutrinos that IceCube could then detect.
It's just incredible. To solve the mysteries of the sun, you have to look down into the Antarctic ice. It's a very optimistic time for this field.
Absolutely. We're asking fundamental questions and actually getting answers.
Well, here's a final thought for you. As you're sitting here right now, billions of these neutrinos are passing straight through you. They've traveled across the universe, through galaxies and stars, and they're flying through your body without you even knowing it.
You're part of the detector in a way.
You're connected to those black holes and exploding stars.
It's a pretty amazing thought.
If you enjoyed this deep dive, please subscribe to the show. And hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in.